basically an idea where you defend the infrastructure or you ethically attack it. So I've done both for several years, and eventually ended up on the blue side back with basically applying AI techniques for threat detection in Microsoft. And this is the part of my life. Another part is more academic, because I believe kind of scientific method is the ultimate, I don't know, best thing that we can have as humanity, right? So I believe the advancing it is still good. So I've done 2 master degrees and have 2 of them, and right now doing the PhD in a perfect combination of Italian universities. So yeah, for fun and profit. Some of the certificates and conferences, just to recap. But yeah, basically our agenda today, we will go over several topics, and I hope you will kind of relax, take your tea, and enjoy it without really like digging into as in a lecture, more of like a story. So we will start off with a threat model. In security, threat model is basically an idea how to assume the attacker's capabilities, like threat actor capabilities to attack you, and what are the defenders are capable of within this threat model. Then we will jump to the alternative topic, which is a self-supervised learning, and we will see how it potentially can help with the threat model that we kind of see in the realistic scenarios. Then discuss the malware detection, and then the actual experiments and the results within the scope of the previous discussions. So yeah, let's start with the threat model. So in conventional research, as you can see in academia or maybe many public discussions, lots of attention goes solely to malware, right? And the malware, those are like exe files or DLL files, which are generally called PE, portable executable files. And it's pretty mature in discipline. Since 2022, we have more than 16,000 publications. And actually, I made this image, I believe, several months ago. So now it would be even more. And it's pretty solid body of literature. But the problem is that actual threats are more widespread. And there are many ways to compromise the system without really relying on P files. And malware research is mostly focusing on only this subset of the threats. And yeah, there are many ways to run a malicious code on Windows system. There are Linux systems, right? They have their own formats and ways to, yeah, run malicious logic. Even more, there is a so-called living off the land techniques, which are basically using a legitimate application already present on a host. So threat actors don't need to upload any malware at all, any malicious code. They just use what is present there. And how to catch this behavior? You surely cannot do this from just analyzing the applications then run. And the answer is system logs. System logs basically are behavior of a system, like a human does something, and you can see from his behavior what he's up to. The same can be applied to the system, any basically operating system, application, or something. And yeah, these system logs are good body of truth for any AI application. And the techniques that you can explore in one domain due to the structure of system logs should generally kind of apply to many sources of logs because of their similarity. And how like modern, really practical and real world security operations handle this in those, this is called security operations center, where people actually are sitting and monitoring the infrastructures to understand whether the compromise happens. Those system logs are fed into some of the solution. Usually they can aggregate it under the umbrella of CM, which is security, incident, and event management. And within a CM solutions, there is a detection engineering. Basically, you build some heuristics on top of the system logs that later are used to throw an alert for an security analyst. And those alerts already are investigated manually or with some extra logic. But basically, system logs are this ultimate truth for majority of organizations to defend them. And how system logs look? they, as I mentioned before already, they are kind of similar in a structure independently of a system. This is a machine language, to the contrary of the natural language that we hear often. They have short machine data strings. They have practically all the time key value structure, has a timestamp, and lots of and tons of unnecessary values like process IDs, hashes, which are maybe valuable, but those are completely arbitrary. So yeah, what are the challenges if we take this data and try to apply AI techniques? As you will see, we will need actually a MISIX or something like that for that, because it's completely impossible to do just in human way. There are hard to acquire supervised data sets for the logs. First of all, it's hard to answer what to label. It heavily depends on the application and many other nuances, like whether you take a single log entry and label it, or you label all the data from compromised machine. But if all, then within what time period, 1 hour, 1 week, and it's hard to chunk them, and it's even more, it's expensive. It takes a significant amount of time of highly trained people to do this and get really single label, several human hours. So and data is huge. There are literally terabytes of logs per day in just middle business organizations. So yeah, it's so many problems with that, and that's where potentially self-supervised learning can come in as an answer within a next several years. Let's take a look why. Before that, let's step back and maybe since I believe the audience is mostly the AI oriented, and this picture should be at least vaguely familiar for you, that like back in 2016, 5-7 years back, every domain has its own state of the art, right? Like custom solutions that was the best for different domains. Right now, state of the art looks like that. It's like transformers everywhere, right? And just throw the more computing power and it will work. And it's good and bad. There are pros and cons, but the interesting point that significant part of the success in those transformer modeling solutions comes from the efficient adaptation of actually self-supervised learning techniques. And how this comes and how is this possible? Probably, if this is familiar, excuse me, but I believe it's good to go over the steps how those models are trained to, in the general sense, to be on the same page, right? At least terminologically. So we have this huge unlabeled corpus. I don't know. That's why they say the GPT was trained on the whole internet. Basically, they grab a lot of resources that has just textual data, and they pre-train it using the self-supervised learning. And this is the majority. This is where the majority of computation falls in, like 9% of the computation is through this stage. Then we come to the so-called fine-tuning, which is done as a supervised learning. And there are like different types of labeled fine-tuning techniques. You have question answering, recommendations, and in our case, for example, malware detection, right? And you get this application where basically we get out from the model what we want. And the cool thing that with a single pre-trained model, we can have many fine-tuned applications. And yeah, that comes handy because this fine-tuning is relatively simple. And how actually SSL pre-training, like self-supervised pre-training, happens from natural languages? There are two common paradigms here: GPT-like, which is more scientifically called an autoregressive way, and in an easy words, it's basically predict me what comes next based on the previous context. And here we can assume, for example, our context is nothing, and the next token should be is. And we task a model to predict the token is. When the context is nothing is, the next context should be impossible. And if model predicts it correctly, we go on. If prediction is wrong, we penalize the model with a higher loss. And that's how actually they are trained. Of course, the tokens are more granular, not the full words, but rudely, it is that this logic implied in the pre-training of GPT-like models. There is an alternative for BERT-like models with a masked language model pre-training. And in this case, the self-supervised task masks some of the tokens in an original sequence. For instance, in this example, we mask a word brown, replace it with a substitute token, and we task a model to predict a word brown, and we penalize if the prediction is incorrect, and model slowly learns to understand from the context around this word to guess the correct token. So what are the benefits of self-supervised learning? And this will be a quote from a perfect, really source of information on this topic. And you see at the bottom of the slide, basically a cookbook published by Meta's AI team. So first of all, self-supervised learning allows to extract the structural information from huge quantities of unlabeled data. So no labeling needed. And that's really correlates with the previous observation with the system logs in the current modern cybersecurity space. We have terabytes of them without really good analysis. Another point is that SSL learns a generic representations, and especially valuable where domains in domains where labels are costly or the specific task cannot be known. So first one, labels are costly, exactly our case. Moreover, the task cannot be known. It's interesting bullet because in security, you have those so-called 0 days vulnerabilities where you actually don't know what attacker will exploit. So SSL techniques actually can bring some value in preemptive prediction in this domain, preemptive detection. And the last bullet, there is evidence that SSL produce more robust representations towards the adversarial examples. And for those who don't know, adversarial examples is a case where assumed threat actor, assumed adversary, somehow perturbates the input to the AI model, and it completely screws up the behavior of the model. And it's assumed to be kind of some sort of threat actor or attacker of a model. And guess what? In cybersecurity, we have this type of assumption by default. Cybersecurity solutions have an adversaries facing them. So SSL here might help as well to build more better solutions. So that was the most burdensome slide of the talk. It will be lighter now. And but jumping one more evidence towards the feasibility of SSL solutions for cybersecurity might come from the fact that we actually don't need really large models and that are too general. There is evidence, and a lot of people influential in a domain, authoritative in domain, see a huge potential for a small language models where more cheaper specialized models make more sense for a narrow applications like cybersecurity, because it's not a general case that we need to ask everything. We have to ask specific questions to this model, whether something suspicious happens on this host, whether this is unusual, whether this corresponds to known malicious activity. And the actual small language model might be much more valuable than huge, large, I don't know, monster that is running on tons of GPUs and takes like thousands of dollars per day, like existing ChatGPT solutions. Why we are talking about malware here? I will show you that malware is a good proxy task for inferring what works for system lock inference, and specifically dynamic malware analysis here comes in. And let me show this in a more systematic way. So we wanna, like, their ultimate goal of modern security world would be to develop a good self-supervised learning technique for system locks. Well, something that we built for natural languages in a form of GPT, but for example, Windows. The model that understands what happened on a Windows machine or Linux machine and says, yeah, this machine does something that is regular, or this machine does something bad. But the problem is there are no benchmark data sets in this domain. There are this is because the many system locks basically correspond to the behavior of infrastructure. this is a sensitive data that people don't want to share, and this is understandable. And a poor body of literature. There are publications, and those who publish there do a great job, but it's comparably scarce. So what if we take a basically rich domain of malware detection and explore self-supervised techniques there? Datasets exist, public malware collections are there, rich literature, and we evaluate on a smaller set of models and data relative method performance, which method works better than other method. And we find out some good self-supervised learning techniques there, and we basically transfer those to the system logs on a more data and scaling up with actually smaller supervised datasets. So why dynamic malware analysis? Let me explain to you for those who are not familiar with this, I don't know, subfield or subdiscipline in security. It's basically when you take an application, for instance, in this case, of exe or DLL file, which is practically the same from the operating system point of view, and you pass it either through a sandbox or emulator. One is sandbox is more full than emulator. It will produce a more rich representations, but it has its own drawbacks. And eventually, what we get a behavior of malware or application in a system, like parent process relationships, command lines it executes, API calls, and registry access, network access, and many more. So this actually resembles a lot what system logs bring to us, and it's practically the same information, just acquired a different way. And here, for this work, I chose to use an emulator because of its ability to produce results fast and iterate over the samples really faster, because sandbox is a costly. It's basically you have to boot up a VM, emulate it, collect sample, revert VM, and go over and over. And this is not feasible for like hundreds of thousands of samples. Whereas emulation is, there is a good solution proposed or released and maintained actively by Mandiant, one of the, I'd say, best cybersecurity companies in this space. And it's as easy as 4 lines of code, and you get a dynamic report from a PE file in basically 4 lines of code. And how the emulation report looks like. You have a traffic, you have a registry access, file access, and API calls, and pretty decent information that is rich and resembles a lot what we get in the system log format. So this is the thing that we can model, right? So let's take a look how this can be modeled with AI techniques. Dataset. I collected this dataset basically myself as well, and yeah, it corresponds to roughly 100,000 samples, 93,000 to be exact, spanned across time, with a training set collected in January, test set collected in April to reflect so-called concept drift in a malware. And yeah, it has both malicious samples and clean samples, and is pretty decent in this case. So if you are interested in this kind of topic, you can download this data set. It's publicly available. Model itself looks as follows. It's maybe pretty scary at this point, but for instance, the first part we already discussed. You have to acquire a behavior in some way, and it's either a dynamic analysis through sandbox or emulator, or it's some of the operating system logs that can be as an alternative point of input. So we get the behavior here. Next one, I would stress that we need a data cleaning for system logs. We just cannot take a natural language way, like in case of natural languages, English, French, you can take a text and it's already informationally rich, and you don't really need to extract a lot of data by yourself. The model will capture the semantics. However, in system logs, I would say that's where the domain knowledge comes in, and you still have to filter stuff out from the system logs. Let's take a look. For example, the dynamic report on the left. first of all, if you just get all the data, it's too much. It's too much of the sequence length would be for an expensive model like transformer to handle. For example, consider if we don't, this graph, on the x-axis, it has a number of unique tokens within a data set. And if we don't filter anything out of the reports, we just take it as is, tokenize, there are almost like 1 million unique tokens in my data set. And it's relatively small data set. So, however, if you filter, for example, only API call names, it's 20,000. It's orders of magnitude difference. And it basically emphasizes how verbose are some of the arbitrary values like file hash or memory segments. You don't need to feed them into the model. And that's where some part of the domain knowledge might come in security field. So some experts should know that this is not relevant, we filter this out, and this is relevant, we preserve it. And so yeah, those fields, we strip them away, and we see that if we take away those arbitrary values, the actual performance is much more stable. If we don't, this blue line, you can see how huge the standard deviation is on a test set here. It means that that model severely overfits to some of those values and really fluctuates depending on the test set. Whereas if we filter them out, the performance is first of all much higher. This graph is a ROC curve, and the higher is ROC curve, the better, roughly saying. So we first of all see that it's significantly higher, the green line, and the second, it's much more stable. So we don't need those arbitrary values. And if you apply AI modeling techniques in your domain that has similar patterns, those arbitrary values are probably not needed. So in our case, for aficionados, those that are deep maybe in this topic, I just want to mention that we preserve an API calls, file access, network events, and registry access. And those 4 types of data is enough for the model to basically give the best possible predictions. Next bullet point here is that during the cleaning stage, we need to normalize data. And what by normalization I mean is manually replacing some of the common patterns with the placeholders. For example, the hash is completely arbitrary. It's like cryptographic function, which with the difference in a single byte will produce a totally different value. And this is irrelevant for a model. When it tokenizes it creates just a unnecessary sequence of tokens. And it's better to replace this whole value with a single small placeholder that model can learn and use to infer. For a security specialist, the file name that is called hash.dat is a red flag. However, without the normalization, it would be pointless for a model. And this applies to other fields that are sort of common to know, like IP addresses, which are basically key values as well. So you don't want a specific numbers in an IP address. You want more of a general representation of what this IP means, whether it's public, private, or something. And yeah, so we implement some of the normalization here as well. It's public, and you will see, I will share a code by the end. So if you are interested what exactly we do here, you can take a look on code. So yeah, we have a data cleaning. Now we have a cleaned and normalized data. Then we go to the feature extraction. And yeah, it's basically tokenization and encoding. And if the folks are here mostly AI background related, with this point, we basically start overlapping with natural languages higher and higher. So here, what we take a JSON and just flatten it and take token by token. Not all tokens are taken. Some of them are stripped away because we don't need model to attend to the common value that is always at the same place in a sequence. So for example, we strip away some of the keys. And another bullet to say that we don't always tokenize in a white space domain, as I show in this example, because it's easy to understand. You basically see how it's stripped by spaces. We tried a BPA encoding tokenization, excuse me, which basically is what GPT-like models use. They use byte pair encoding tokens, which is more about database-based way to tokenize. It basically takes a huge unlabeled corpus and statistically sees which characters occur often, and those place higher in the vocabulary, therefore making the kind of more valuable tokens for the model. However, our our empirical evidence shows that basically both types of tokens work similarly, with some cases, in some cases, for example, white space even outperforms BPE, but not always. Yeah, and encoding is straightforward. You get the vocabulary encoding, and then you get to the modeling part. And I will not go deeply in what it does. It's basically a transformer, and it's really almost one-to-one replica with what we have in natural languages. Nothing too fancy, and at this point, it resembles the natural language modeling task already. One difference is here is that we use the encoder part only to get a representation, and this encoder part is doesn't have a global attention, but is a kind of sliced attention windows, which again, based on empirical tests, we see that for this data, this type of attention work the best. So yeah, let's jump to the results and what this approach promises, and maybe where we go with it. So in purely supervised manner, so there is no pre-training. We just use a supervised data only. We just wanted to compare this method with an alternative methods that already exist without the advantage of self-supervised learning. And we see even in that setting, our model here is Nebula, the blue one. And we see that it kind of outperforms other methods significantly. Again, this is a ROC curve, and the higher is better. And if we take, for instance, a specific false positive rate, like 10 into power of -2, which is like 1 false alert per 100 examinations, we see that our model detects on this data set closely to kind of 70-something % of samples, whereas the closer alternatives detect much lower. And again, this is noisy data, and it's like subset to improve those metrics. Those are relative. The matter here, the relative performances. To get the absolute performance up, you just need to scale up the model and data set. So those can be expanded to more of a production-ready solutions like 99% detection rates, which with the higher data sets. But we already see that relative performance is better. However, if we switch our attention to the pre-training, let me explain first how we set up this experimental run. So we have the training data and test data, right? Training data collected in January, test data in April, and the sizes are 25,000. We take a large chunk of the training data, for instance, 80%, and assume that this is unlabeled corpus. We strip away the labels, and we use it only for pre-training. Then we pre-train the model using this unlabeled part of the dataset. And in our case, let's start with the masked language model. We took a sequence, as we've seen it before, and we basically mask some of the tokens and just ask the transformer which tokens are masked and guess us back those. Run for several epochs, and then we fine-tune this model on the small supervised dataset. And this small supervised dataset is the rest part of the training set. And then we evaluate how well it performs on test set compared with the model that haven't seen this blue chunk without any self-supervision. And this is the result graph. So here again, yellow line is the performance of model that's seen just this yellow chunk, so it's lower bound. We included still upper bound performance, which is the green. We assume that how well performed the model that seen all the data with all the labels, that has a pure knowledge of our data set. And basically the blue line corresponds to this pre-trained model, depending on the size of this unlabeled corpus. So we artificially downscaled it to be the same size as the supervised dataset, and then we gradually increased it to the full size. And what we see that that at least this preliminary evidence shows that way, even from system logs, the model is capable of inferring the information from unlabeled. And really striking here, at least from this experimental run, is that in the case with when all this unlabeled data was used, the performance almost matches the model that had the labels. So it's as if the self-supervised logic was as good as a purely supervised. So, and taking into attention that getting the unlabeled data is super cheap and we can scale this up further without any cost involvement of human analysts, this might be a really promising direction with this LR approximation going over potentially what we could get with labels. Again, this is a relatively short run on a small data set. I would like to replicate it from different scenarios with a larger data set, with the, kind of explore it more cautiously, but it's kind of first evidence here that this is a promising direction. Another point here is we've compared as well the autoregressive GPT-like pre-training with a masked language model pre-training. And interestingly, the autoregressive one takes significantly higher amount of time. Here you can see in a graph on the x-axis is the time. And if we take a look, for example, 2 epochs over our data, for masked language model takes only 15 minutes, whereas autoregressive takes closely to 2 hours. And it might say that autoregressive is more richer in a sense that it extracts more data or more information from the same data. However, we are not sure, and like first sort of runs that we've done recently basically show that masked language model, even with this low, like smaller amount of pre-training, is slightly better than the autoregressive. And those are the learning curves of true positive rate. And yeah, we want to explore this more. So yeah, do we have time? Maybe 3 more minutes. I want to discuss about the explainability of these models. And this comes as a bonus from the using transformer for malware detection, which there is some kind of speculative discussion, which is not like ultimate, that there is some opinions that attention weights are not really explanations, but it still gives some interesting points of view on what the model thinks about the parsed sample. And we took just a random cherry-picked, not cherry-picked, actually, it's basically first sample that we took from our data set and analyzed what the attention weights show. And one of the strongest activations was between the 2 tokens, exadose and getTcount. First is sort of an oxymoron stuff. It's not present in a default system. Exadose is non-existent in a Windows system, but it's interesting play between 2 components, exa, which is common, and dose. And this malware uses this string to drop a temporary file. And model thinks this is highly correlated with malicious behavior. Another one is a getTcount. And getTcount is basically an API call that malware authors use for anti-debugging technique. It's a way to understand whether the malware is being executed in a debugger, and if yes, you halt the actual behavior, so kind of reverse engineer cannot get it back, or like sandbox cannot get it back. And there are actual manual rules written by security like analysts to detect malware based on this API count. So it's interesting, and it might be used as a complementary component of this model, maybe inferring some indicators of compromise or something. Another point is that the attention activations sort of indeed correlates with the well-known explainable AI methods. One of the good methods is integrated gradients, where you compare the one labeled input towards the baseline input, and you check which features are strongly correlated with the label that kind of model produces. And we see that it sort of really resembles what attention weights show. And in this sense, kind of our empirical evidence shows that you can trust attention activations to infer something. And this might be a valuable component, for example, for security analysts doing an alert investigation to maybe show the most strongest activations and say, yeah, these are the indicators why our model thinks this file is malicious. And the kind of reverse engineer has something to start with already. So yeah, the very end, we will throw some maybe future work ideas. And one of them is actually sort of interesting guess that we have is that I would say that existing techniques that we tested, autoregressive and masked language model, are not the best ways to pre-train on system logs because of the structure. It's arbitrary. It's not like natural languages where the single word changing value of single word in a sentence will completely screw out the meaning. In system logs, changing a single value might preserve the log's kind of semantic structure and all the meaning there. So we think that there might be better ways to model, and some of the influence can actually come from the computer vision domain, like diffusion models or other solutions that are like significantly progressed as well in the latest years. For instance, bring your own latent might be a good starting point here. And by defining some of the augmentation techniques on system logs, we basically maybe even can reuse one-to-one these methods on the system logs. So yeah, this is wild guess, no, like purely speculative, no evidence whatsoever, but if you see her potential, yeah, feel free to reach me out. So yeah, basically a last slide. About availability and reproducibility. All the data, all the code, all the experiments, and the results are available publicly. It's on GitHub, the Trizna Nebula. You can install the model with a pip and run it right away, again, with a few lines of code, as you see on the right. And the like technical paper on the supervised part, no self-supervised yet, but we published all the experiments on the supervised part, is available on Arxiv already, and we are going to peer review stage, but yeah, it's kind of preprint is there. So yeah, that's it. I hope it was interesting, not too fast, maybe around two really like over the concepts, but yeah, hopefully it was fascinating. And if you see any questions, I'm open now.
Thank you very much for your very interesting talk.